Welcome to APEC. It's December 10th, and I'm your moderator, Tim Ventura. First, I'd like to thank everyone for joining us on this call, along with everyone watching us on YouTube. In today's session, Justin Pearson will be discussing Baldwin Aerospace and their approach to hypersonic MHD propulsion. Greg Hodgin is going to be talking about the ZC Industries warp drive. And then Mark Sokol is going to be demonstrating a rebuilt Podkletnov Impulse generator experiment. This is going to be a retest of the one that we did at last conference. Todd, Desiato, and Mark are also going to be demonstrating a completed version of the ion drive that Todd has designed. And Michael Perrone will be discussing the second law of thermodynamics. He's actually working on some projects based on that as well. We will be finishing off the event with open discussion as normal and ad hoc presentations by conference attendees if they are available. So a couple of quick reminders. You can view conference replays, details, and speaker info on our website at www.altpropulsion.com. Please save your questions for the Q&A session after each presentation. We're doing things a little bit differently now. We're not giving a full hour for the Q&As anymore. We are doing much shorter sessions when available. Please raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can type your questions into chat as well, and we will try and go through them after each presenter finishes. So I want to introduce you now. I'm really pleased to introduce Justin Pearson. He's going to be describing the Baldwin Aerospace solution to the problem of hypersonic propulsion. He'll compare Baldwin's programs to Hermeus and describe MHD propulsion, followed by his plans to utilize this technology. He's going to be providing some details on how the technology stands out for the competition. He'll be providing some engineering level overviews as well as some business information. So he's going to try and cover the entire scope of what's being worked on there. He's also going to talk about the team that he's put together to help solve these challenges. So that is his presentation, and he's going to be getting started now. Let's everyone welcome Justin to today's event. I want to hand things over to him to get started.
Hey, Tim, thank you so much for having me. So I was excited to kind of do exactly what you said, provide a holistic overview of Baldwin Aerospace. I represent 19 people at Baldwin, and I'm going to get into the engineering or the business overview, but I think I'll first start off with my story of how I started the business, what got me interested in aviation aerospace. And I think I'll start from the beginning. I grew up in a small Midwestern town in actually underneath the downwind traffic pattern of a small airport. Basically, the most vivid memory I have is looking up and seeing just like A-10s or B-2s flying over my house, basically, or Cessnas. So that was my introduction to aviation. And I pursued in college that passion for, I wanted to be a pilot. I wanted to get into commercial airline. So I got my pilot's license. I had an idea of what I wanted, but still it wasn't exactly what I had in mind. And I think everyone here can kind of relate to the idea of you just want to do your own thing. And that's kind of what got me into starting my own business. And that was about 5 years ago. Basically, I had an idea of, I wanted to spend a year in figuring out what niche market was available for the aerospace industry. So I kind of was interested in single stage orbit engines, reactive engines. So that was kind of the beginning. And I took that year, I started with like rocket books, textbooks, detonation propulsion, kind of just would spend 7 hours a day reading. So I think a lot of people here can relate to just, there's something that you like, you just teach yourself it. And throughout the following years, the second, the third, the fourth, the fifth year, that vision of single stage orbit engines kind of evolved and transferred into a passion for hypersonics. And right now, Baldwin, as it stands, is a propulsion hypersonics business, a research and development of advanced propulsion, hypersonic technologies, and that is where that's where the 19 people, that's our focus. And working with engineers from California, North Carolina remotely, and looking towards the future. And I'm going to share my screen. Tim, I'm going to start the presentation. Let's see here. So again, I'm going to start with the overview of Baldwin, and then we'll get into some more details. So I think you can see this. I'm going to move this chat bar over. So
yeah,
right.
no, it looks great. Sorry to jump in. It looks great. The slides themselves are a little small. If you're able to make those a little bigger.
Okay, let me check here.
It looks like it.
Okay, this first slide, Tim, is a little bit smaller. I think once I go through, they'll become larger.
Okay, yeah, I just wanted to let you know. It looks like they're not maximized. It's showing multiple screens. There we go. Okay, sorry, let me mute myself out. Sorry, sir.
No, you're fine, Tim. Just jump in if audio cuts out or something. I appreciate it. So the name Baldwin Aerospace comes from this area, this region of the world. You probably, I'm a fan of history, fan of the Crusades. And if you've ever heard of Baldwin IV, King of Jerusalem, the Leper King, that's the origins of the name. But also the logo was put together by Chris Lee, and kind of a focus on the obscure part of the world. And that's kind of the way I describe Baldwin. It's supposed to be out of left field, not expected. And this is going to be an overview of some of the stuff we'll go over, but this is Baldwin's team, executive managers. There's 19 people at Baldwin currently, and I can't stress enough my thanks and gratitude to the people that sacrifice. A business like this, it really requires sacrifice. People volunteer their time away from family, friends, during holidays, late at night. A lot of times we're in meetings for 2 hours at night. So I think everyone here again can relate to that. Tim, definitely you're the one who's the most busy. So again, we'll be looking at the competition of the programs and comparing those to Hermios, the scramjet challenges, energy edition, MHD, and then something we're doing kind of to turn things on its end, to kind of add to what we imagine like a hypersonic technologies. We'll also look at perspectives, timeline of Baldwin, team, real world challenges that an aerospace business face, and the partnerships and future goals of Baldwin Aerospace. So I'll start here with, I'm pretty sure everyone here is familiar with Hermios and what their platform is. They do have the quarter horse. This is their fuselage design, right? So it's 40 feet long. It's an unmanned vehicle. And it's the test fuselage for their propulsion engine, the Chimera. And this is a turbine-based combined cycle engine. Interestingly enough, it's not complete legacy, but it relies on legacy technology for their GE J85 21 turbojet core. And it's kind of like a turbo ramjet at top speed of Mach 5. So if you compare that to Baldwin's programs, we have a test fuselage, the Arbiter, and 12 feet in length. Now, we also have a propulsion engine, the Midnight engine, and the Arbiter is the test fuselage for the Midnight engine. Now, this is a scramjet, so a little different than Hermios's Chimera, and it doesn't deal with legacy technology. So we're not dealing with the compression stage, dealing strictly with hypersonics. And we'll go into this a little bit later, Baldwin's novel combustion chamber core. That's my current focus with the engineering team at Baldwin. And even some differences in the speed. So we're looking at a cruise speed of Mach 7 plus. Even so, I think anyone who's familiar with scramjets and flight profiles, there's the question, okay, how do you actually test this? how would you ignite an engine like this? And we're not dealing with a turbojet like taking off from a runway. So there's a difference in how you'd relate to the testing phase of Baldwin and compare that to Hermios's. And I can get into that later. But again, here's a greater breakdown of the programs at Baldwin. The Arbiter, if you kind of even compare the dimensions of this program. So 8-inch diameter, 12 feet length, that's very telling if you even look at 40-foot length quarter horse. And that's something we'll see. Obviously, when you deal with the inspection at MHD, you're reducing size, hopefully, and reducing weight. And then the Midnight Engine, a propulsion unit that solves the problems of hypersonic flight. And that's a simulation of the Midnight Engine right there, simulated at Mach 6. And the focus right now is obviously simulation and CFD, working remotely with the engineers. For the audience that isn't familiar with scramjets, here's a little bit of a breakdown. So we're dealing with a vehicle traveling Mach 5 plus. It's consistently consists of 4-body inlet, isolator region, combustion chamber, nozzle. And really the scramjet, the hope is dealing in scramjets in this flight profile, but then extending this. So extending in altitude. Really, scramjets now are limited to a very small flight profile. And kind of like I said earlier, in how we would test the Arbiter, you're even limited in that. Here's a test that Northrop Grumman did of their 18-foot scramjet engine. It endured 30 minutes of total combustion, produced 13,000 pounds of thrust. But even this, how can you fit this on something that would be the dimensions of the Arbiter laid out? So you can kind of say, again, EM spectrum, the hope is that you reduce size and weight. Now, the challenges of hypersonics, I think everyone here is familiar, but for the audience sake, the aerodynamic loads on the fuselage. So this picture kind of goes into a little bit of depth of the complexity of the issues that you deal with in hypersonics. So aerodynamics loads on the fuselage, thermal loads, that's probably of the top two, that's one of them. Insufficient thrust, that right there is probably the greatest. MHD has one of the greatest, can provide the greatest effect in this area, insufficient thrust. Combustion time, trying to light a candle in a scramjet or in hurricane. That's the common illustration used. So the shock waves that a fuselage like this would experience in flight. This is also a common problem that will be used against hypersonic vehicles in the commercial sector. So dealing with the shock waves, the sonic booms, Hermios, boom supersonics. These are all businesses dealing with, can you get a commercial airliner that's traveling supersonically to travel over land? So there's about 600 flight destinations from the US that are traveling like over the Pacific, over the Atlantic, that aren't traveling over land. But how can we get hypersonic vehicles traveling over land? Well, we have to solve the problem with shock waves and sonic booms. Then we saw with the Northrop Grumman example, a weight of the vehicle, especially again, the size and dimensions of the Arbiter, the reaction time. So if you want to turn hypersonic fuselage traveling Mach 6, 7, 8, you're going to turn a certain amount and you're going to be miles off if you miss. So again, I think everyone's familiar with those challenges. But what are some of the ways that people have tried to solve these problems? The most common is obviously throwing mass at the problem. This could take the form of, okay, you're going to just use ceramics, you're going to use material thermal protection systems, or you're going to use a physical ramp in the inlet. You're going to use like a fin to vector control. we're going to talk about a way to solve these problems using energy addition and MHD. And then we're going to go a little bit beyond that. And keep in mind, again, we're applying MHD to scramjets. This is our focus, and not reentry vehicles. So we'll make that clear. So what is energy addition? Again, for the audience sake, we're going to add energy into the system using a multitude of ways: electrodes, microwaves, lasers. Here's a electrode forming a plasma. The benefit is you can reduce drag. Okay, that's good. You can also increase the inlet mass flow. A common or often overlooked benefit to energy addition is you can create a heated region, which will increase the mass flow into the inlet. Now there's drawbacks to that as well, but I think it's the way I look at MHD, or in this case, energy addition. It's a great technology that's really a stepping stone into other technologies, because this is a holistic. If you want to solve these challenges with hypersonic, you have to look at it holistically. And then this is again kind of a layout of what that would look like using electrodes and forming a plasma region. Now, what is magnetic hydrodynamics? And this is really where we're getting into Baldwin Aerospace's focus. So it's the process by which ionized air can be controlled using magnetic fields. Anybody ever watched The Hunt for Red October, the Caterpillar drive? That's used in more of a marine environment, like specifically like cavitation of propellers. So again, we're not talking about that. We're talking about aerospace application, and because you need an ionization source, and this is that energy addition. You also need magnetic fields. It's not a new concept. 1950s, 1970s, 1990s, 2010s. It is a maturing technology, though, that is entering commercialization. Basically, between now 2022, this is December 2022, and 2030, there'll be real-world applications for both defense and commercial. More commercial would look at, okay, we're going to, a common illustration is used for commercial airliners in controlling or like turning, things like that. But there's also problems with, okay, making this technology commercially acceptable. So what is magnetic hydrodynamics? We're going to a brief overview of that. MHD tackling challenges in hypersonics. So you could theoretically, you could use it as a shockwave boundary layer interaction. MHD can be used to reduce shock-induced flow separation by decelerating flow via the Lorentz force. And that's what you see happening right here. You have a separated bubble. Using MHD, you can reduce that, decreasing or eliminating the adverse pressure gradients, separation. This improves hypersonic flow. Another use is MHD thermal protection systems. So thermal loads on the blunt body can be decreased by fine-tuning the magnetic field in the region of MHD interaction. This is reference one. The ionized airflow is diverted by the electrodes. The direction of the diverted flow in the presence of a magnetic field causes the Lorentz force to move the shock waves away from the body and reduce thermal loads. And on the previous slide, you saw a picture over here on the right. That's represented by picture E here in the bottom left. And you can see the shock wave formed on this reentry vehicle extending farther away from the body. So again, multiple uses for MHD. Now there's advanced usage for scramjets. And this is really where, again, this is the picture you see is of the Ajax 1981 Russian model. And this is Baldwin's base. Obviously, there's things that are different in how we're approaching this. But for illustration purposes, you don't really have to focus on everything that you see in front of you on the screen, but more specifically, the MHD generation and acceleration. So these purple boxes would represent where in the front, in the inlet area, where they're going to pull energy out after it's been ionized. So you need a 2500 Kelvin MHD effective temperature, ionization source, usually lasers, microwaves. This is the energy addition. could be electrodes. So they're going to pull energy out, and in what's called a energy bypass method, they're going to use that energy to accelerate the flow in the nozzle. That's what we said the MHD uses for propulsion. I've talked with some PhD candidates funded by Lockheed who actually are working in MHD acceleration. So this isn't a new technology, but the reverse of the energy bypass would be the reverse, where energy is pulled from the nozzle and funneled towards the inlet area. Now, I know you can read it, but for those listening, it's MHD power extraction has the potential of providing hypersonic vehicles with high power capabilities. Modeling efforts indicate that power levels on the order of megawatts per square meter of active panel area can be achieved on reentry vehicle surfaces and in the exhaust region of hypersonic scramjet engines. These power levels will require that seating with alkali metal vapor at 1% level be incorporated. So even now, the question is, okay, can you solve the problems of hypersonic flow with just energy, with lasers and magnetic fields? No, you kind of see that here. You need something else. You need a physicality to it. Next slide is, so I have to move my Zoom. Next slide, MHD power requirements. So to ensure that the MHD interaction with scramjet inlet, we must use non-equilibrium methods of plasma creation like we saw with energy addition. Thus, in the MHD controlled inlet, a part of the power produced by the MHD generator needs to be spent on sustaining a non-equilibrium conductivity of the flow. What does that look like? Well, they're going to pull out a certain amount of power, and that's going to be used as an ionization source. Over on the right, you see a typical MHD generation. Now, over here on the left, again, this is put together by Andriy Starokovsky from Princeton. I've talked to a few people over there working in MHD generation. Very interesting. Now, there are shortcomings, and this is where Baldwin's focus is becoming even more clear. Shortcomings of the Russian Ajax is, so if you have the ability of the MHD inlet, so rather the ability of the MHD inlet to control inlet mass flow and to extract and dissipate power can provide control of the scramjet entrance thermodynamic state. Thereby providing the potential for increased scramjet operating range. That's what we said in the beginning. We want to increase the scramjet operation range, this area, and improve that. So how do we do that? We need more power. And not enough power can be generated to fly the Ajax in a real-world scramjet flight envelope. And I liken it to the kind of the Ajax is kind of like a glass half full, whereas and that's the illustration of the power that's needed or produced. Whereas we want, the ideal situation is to provide a source of power that's overflowing. To power auxiliary units, to power the ionization source, to increase thrust, kind of like we saw with the Ajax through MHD acceleration. And this is kind of what the most important part of the speech really is. Baldwin will attain this power by generating higher energy densities. And what do I mean by that? Well, this is kind of this is an interesting slide. It's a discovery mission. So whether you're looking at I'll say it like this: Baldwin is really a discovery mission because you're dealing with the underdog, or you're dealing with people that, again, we're combining what you imagine is the typical classical aerospace engineer with someone that is inexperienced. And you're going to see the team that we're assembling is really representative of that. And I wanted to pull examples of personal stories that have inspired me, of people that kind of went out and discovered. So, Armstrong, Ford v. Ferrari, kind of the underdog, or the movie October Sky, I'm sure everyone's familiar with that. But obtaining those higher energy densities, this discovery mission, it's not a new concept. It's higher energy densities occur in several fields of physics and technology. You could look at astrophysics. You could look at nuclear weapons, nuclear energy. Reactions are broken down into four four methods: chemical, you have nuclear, electrical, electrochemical. And Baldwin's team of engineers have experience in developing technology that can help withstand higher energy densities. And this will help us solve the energy challenge that you saw, or that we brought up back about the Ajax, and improving the flight envelope. I do think it's important to reference that we're not talking about 2015 Boeing's self-sustaining laser-powered nuclear fusion jet engine, the patent that they have on that. And this is also isn't nuclear propulsion. And this is what I meant about assembling the team. We plan to solve the challenges in hypersonics using energy addition, MHD, and we've laid that out in higher energy densities. And solving these challenges require a team with a diverse set of skills. So people from a spectroscopy background, a lasers background, plasma physicists, nuclear engineers, fission, fusion, plus a wide array of interesting engineering disciplines and fields. So theoretical physics, quantum physics, condensed matter physicists. So the result of that is Baldwin Aerospace really resembles a privately held combination of what you'd imagine Lockheed, the programs they're in, Sandia National Laboratories, Los Alamos. And I'm not trying to, so there's good connotation and bad connotation for either. But what I am trying to portray is the goal is a team that can approach the problem of creating higher energy densities from a holistic perspective. Does that make sense? Already. When you do that, though, you run into, there's a few problems that you run into. Because a few days ago, I had a meeting with a nuclear engineer, a plasma physicist, an MHD person, then a few of the other engineers at Baldwin. And you run into the problem of everyone wants to focus on solving the problems in a completely different, they want to look at it through a completely different lens. So how do you describe what we're working on? Well, to some might better understand it through the lens of we're creating a scramjet combustion chamber and relatively easy geometries dealing with aerodynamic loads. Some engineers might better understand it through the lens of this is an MHD generator. And then again, some might look at this problem and say, we're looking at it and it's a small modular reactor, not nuclear propulsion, obviously. I think all would be right. And it is somewhat in the realm of we're figuring out what that is. It's kind of the combination of all. And again, the challenge is how do you select the simulation tools that you're using in modeling the arbiter or modeling the midnight engine? What language do you use when you're trying to get a nuclear engineer to talk with a plasma physicist? Because when I've had meetings where nuclear engineers are great at modeling ionized flow, but they're terrible at hypersonics and vice versa. And so, but also even the strategies. So how can a nuclear engineer, how they would build their systems, how they would build the hardware, how is that different to maybe the roadmap to testing for like a hypersonics or aerodynamic set of engineers? And again, we're trying to combine these perspectives into one. Those perspectives will then be combined into one technology. That's the hope. That's why this is, that's the end goal. And like I said, we're divided, the programs at Baldwin are divided into two. You have the arbiter, and then you have the midnight engine. So the midnight engine, we're focused on designing a novel combustion chamber. And we'll solve the power and thermal challenges, all the things that we discussed so far, of hypersonic flight by applying our studies in MHD, energy addition, high energy density physics, and other disciplines to design the midnight engine. And MHD technologies that we saw are very broad in application. So the same technologies that would be applied in a combustion chamber could be equally applied to the inlet, the fuselage, with the understanding that you can never design a hypersonic combustion chamber, scramjet combustion chamber in isolation with things like seating or even the nozzle. I don't think anybody would design it in isolation, but it's even more, even more relevant even when you would compare that to like design of like a turbojet combustion chamber. Alrighty. You have to have roadmap. You have to have a roadmap of things that you are working on, like actively pursuing. And there has to be a tangible vision and goal to a business. So we do have a path forward, and there's things that we're actively doing over the next couple months and year between now and this time next year. So again, Baldwin's programs divided into two programs. The SBR proposal we're working on through the DoD, a NASA SAA, as well as the 2023 prototype of the Arbiter and the wind tunnel testing at NASA Langley. So really simply, the timeline would be laid out: prototype built early next year, wind tunnel testing fall 2023. And the Midnight Engine timeline is kind of laid out: the novel combustion chamber design simulation, and that's kind of taking place over the next year. And I do have an idea of kind of smaller stepping stone goals that I'd like to accomplish through that. But then you also have over the next 1 to 2 years, those two programs will be assimilated into one program at Baldwin, just like Hermios's Quarter Horse and Chimera are combining into one flight test. I actually think that's going to happen this next year. And then building a propulsion test facility. And I was talking with an engineer this morning. Our goal is not to grow, or our goal is not to swell and grow. You really have, and a dead animal can swell on the side of the road. Only something that's alive can grow. So we're growing a specialized team, not a social club of engineers that can address these problems, but that's also how we're addressing growing a facility. So we're spread out remote working right now, but building a scalable testing facility in the greater Midwestern region in the next 1 to 2 years, working with people that on the team who actually have built facilities like that in the past, or working with people that have actively built supersonic wind tunnels. So again, there has to be a tangible goals. It has to be a tangible form to all of the designs and thought at Baldwin. Now, again, I've already talked about the diversity of the team, but I wanted to highlight something else. It's kind of like when you study this. I'm not a scientist, but I respect the idea of what we can learn from a holistic approach to science. Specifically, like, what can you learn from Hawking radiation in the quantum world, and can what you learn from a black hole somehow be related to the quantum world? And I really think, like the way I described, a holistic team of engineers and that can approach these problems and challenges of hypersonic flight, not a social club, but a specialized team. That's the focus. I don't think I could say it any simpler than that. The engineers that are at Baldwin come from either NASA, Navy, Lockheed Martin, Raytheon, Boeing, Northrop Grumman. They've worked on projects like ceramics at NASA, F-35, U-2 spy plane, advanced missile systems. So that is the team, and that's the programs laid out. But there's also, if we were to talk about navigating the real world and the things that actually happen in the real world from a business perspective that affect the business side of the aerospace world, you really have to look at, okay, other industries, how does it affect the funding? So, and what I mean by that is industries within aerospace, like urban air mobility, a couple of years back were booming, billions of dollars going into them. And now that's kind of with the bottom dropping out of that, not saying that urban air mobility or air taxis or electric flight, things like that are bad, that there's not future or potential in those. That's not what I'm saying. But there's a lot of those industries or businesses that fell, or from an investor standpoint, didn't pan out. And this is December 2022. So in the crypto world, I think everyone's familiar with a well-known crypto giant that recently went under and is under investigation. And that's not related to aerospace, but it is related in the sense that you need to have a plan, a tangible plan. You can't just have hopes and dreams. And even from a smaller perspective, the airline industry, whether you look at it from the electric single aisle airlines, or kind of the problems through COVID that the airline industry faced, there are definite they didn't plan the way they should have. And makes you reconsider what the aerospace business for the 21st century should look like. And it does require a balanced approach. And if you address these real world challenges, there's a misspelling there. I forgot the A. It's not about, it is about removing unnecessary aerospace bureaucracy. Everyone here knows about that. It's, from my perspective, the reason I put this up here on this slide is when I first started Baldwin, it was tear down the system, remove all bureaucracy. Maybe that's not the best word to use, but get rid of all the business practices, things like that. And I don't think that that's anybody's thought here. But after talking with people from the industry, there are certain things that need to stay. There's also certain policies that need to go. I'm not talking about getting rid of policies like FAR-AIM that affect a private pilot. I am talking about things on Capitol Hill like the FAA, or things that would affect the industry in a more broad scope. And this is a profits and policy issue. It's back in the 50s, everyone knew or had a better idea of what was flying above them. Now, no one does, the common person. And it's the common person that votes on the policies that affect the aerospace industry. So in order to address these problems, there needs to be an education process. I think that's what APEC's about too. And again, it is a balance, but the real world challenges like mass production, which is really rooted in affordability. So a propulsion engine, like the Midnight engine, that can be mass produced and affordable for the common man. That's the end goal, I think, for any propulsion unit. You can't have a golden cannon. Also, supply chain. If this is probably the biggest, the greatest roadblock that the aerospace industry is facing right now, even SpaceX or Boeing. This really affects everything. And the hope is to create a more robust scramjet. Think like hypersonic launch systems or Kratos with the Spartan engine. And Baldwin's approach is not just slapping MHD technologies onto a scramjet, but really going down to the singularities, the building blocks of what can we learn from the past 70 plus years of hypersonics? What can we learn from detonation engines or turbojet engines or propulsion, Hall thrusters, ion propulsion, plasma propulsion? And that's why, and that's the team. It's a discovery mission that can answer those questions. And that's the way, when I talk to investors, the business people at Baldwin, don't oversell Baldwin anything but that. And there's also, it's not just about Baldwin too. There's partnerships that need to be in place in order for us to succeed. And we're actively partnering with businesses that can help us with the long-term vision of Baldwin. So companies in the OS software, in particular, this one gentleman that developed F-35 OS, and the Air Force came in and was like wanting to have control, as they do. And he said no. So he started his own business. businesses in the quantum computing world. There's a guy who works with Airbus and has his own business. Machine shops, people that can help Baldwin produce prototypes to get into the wind tunnel testing. Other industries, there's a lot of similarities between hypersonics, and it's kind of like a turbojet can be retrofitted to be in a jet, or retrofitted for a turbo shaft to run a tank or helicopter, or to power a turbine. And the other important aspect that we're trying to bring together is working with funders, investors that have experience and are qualified in the aerospace industry. So people that worked on programs like the B-21, it's a pretty cool reveal recently, even UAV programs. And then some of the other partnerships Baldwin is working with is Datum Source. Basically, they're connected with all the supply chain managers from SpaceX, got so good at their job, started their own business. And that allows us to focus on what we do best, hypersonic propulsion, and work with other people that specialize in those real world challenges the aerospace industries face, like supply chain. And then it's also important that Baldwin can leverage its connections to NASA, the DoD, Texas A&M, other universities like Arizona, who deal with hypersonics. Let me slide my Zoom thing over here. With the hope of, and I've alluded to this, the hope is to address a real world need after we've addressed those challenges. So looking to a road to commercialization, when you talk with an engineer, undergraduate, or PhD candidate, or really anyone, and they go after it, and obviously I know the audience I'm speaking to now understands this, but undergraduate working doesn't, when they go to Lockheed, Raytheon, Northrop Grumman, that technology they're working on isn't going to make its way to the commercial sector, especially with hypersonic technology. So how can you fix that? The defense and commercial application that we're looking at. And again, I already brought this up, other industries. So that Baldwin's best bet for the late 2020s, early 2030s is to look towards the Midnight engine servicing or providing service for commercial single stage orbit engines. Because again, extending that scramjet flight envelope allows things like SSTOs, partnering with commercial airlines. There's a lack of hypersonic propulsion providers out there. So when Boom Supersonics, when Rolls-Royce pulled out of the contracts with them, and they were left scrambling for a propulsion engine, Baldwin down the road could potentially provide that. There's also defense application for NGAD. NGAD is this top secret program that everyone's familiar with, but in the framework of that program is the idea that propulsion units will be used cross-platform. So F-35 or 6th gen fighters, that propulsion engine will be used also in B-21s, or there'll be switchover, there'll be comparisons between the two. And you can kind of see Boom Supersonics over here, their overture, and then Air Force Research Laboratory's representation of what NGAD is. And this is I'm always contacting, or I usually spend about 2 hours in the evening talking with people online. Basically, my goal is networking with people. It's talking with people, whether they're engineers, undergraduate, PhD candidates, senior engineers that are basically retiring or coming out of the workforce. That's, I think, talking with those people and learning from those mistakes. One of the senior engineers at Baldwin was a part of a aerospace startup that failed in 2013. And so what can Baldwin learn from that? Or what can we learn from the successes? Because again, it's a balancing act between learning from getting rid of unnecessary bureaucracy and keeping the things that allow us to compete on a global scale. And there's also a funding aspect attached to that. I have to watch for getting in bed with the wrong people from the money side of things. So I'm going to stop the share real quick and go to, there's a few thoughts and observations. The remaining time that I had, I did want to thank Tim, Mark, Jeremiah, and Jeremy for the opportunity to speak. And again, I represent 19 people that are just passionate about the aerospace industry. And again, these are people that volunteer their time, and they're all at all stages in life. They're PhD candidates, they're undergraduate, they're senior engineers coming out of the workforce, retired, just wanting to stay involved. They're also engineers that were isolated from working at Lockheed. They knew they would never work at Lockheed, but they're free thinkers. So the combining of both parties, I think, is kind of what I'm trying to grow Baldwin to be. And I just have I wrote down some things here just as some quick observations in the 13 or so minutes I have. The first one is, okay, this is interesting to think about. To me, the EM spectrum is the only field capable of dealing with the flows. And the result of that was kind of what we saw with reduction in size. If you compare the Arbiter to programs like Hermios, or even programs like Reactive Engine, Skyline Engine. Another thing is, when you're going down, kind of broader speaking, propulsion engines, when you're going down propulsion path and looking at the different technologies, this is kind of what I did at the beginning of that year when I was trying to figure out the direction I wanted to go in. There's a lot of propulsion ideas that didn't pan out or are kind of not future-proof. So going down to the singularities of, it's not a physics problem, it's just an engineering problem, is kind of my focus in being relevant to the future. That's also kind of why I didn't want to be a commercial airline pilot, because I knew I'd be out of a job in my 50s. I'll kind of end with this story. Throughout the 5 years of kind of growing Baldwin, we really grew a lot for this past year. But when I moved to Kansas City, because that's where I'm located, Kansas City, Missouri, I've got a motorcycle, an R3 2019. So I would always go out and try to meet people and constantly networking with people. That's how I built the base at Baldwin. I would go out every single day and try to meet people. And I didn't really meet many engineers, but I met the business people who helped connect me with the engineers at Baldwin. And it was kind of a referring process. And now that we're kind of growing, it's kind of moved to I network with a lot of people online. And that's where I met some of the engineers. I just brought an engineer this morning who's, again, kind of Caleb, who's kind of a free thinker. He's the guy who's building fusion reactors in his garage. He is inspired. He's the type of person that will basically teach himself anything. And I can relate to that. But I think that's about it. Tim, I know I think I'm ending a few minutes early, but I think that's about all of the points that I had to go across.
No, that's awesome, man. That's awesome. So let me do this. I got a couple of questions here. I want to put this on gallery mode, though. Everybody, enormous applause for Mr. Justin Pearson. Justin, thank you. That's really probably the first, and I think probably the most in-depth. I think that's probably the first and the most in-depth MHD presentation that we've had. I know Will Riken did one, and his was focused on naval stuff. And I think other than that, you're really there in terms of MHD. So thank you. You know, and
that I apologize if it was not as engineering focused as it was business focused.
Well, maybe that's an excuse for you to come back in the future and present more on the engineering side of things. So
definitely, and maybe have some of the other engineers speak on more in depth.
yeah. Well, and yeah, again, from an engineering perspective, and I talked about this with you on the phone. Jean-Louis Naudin did some work that was similar to this on a very small scale. So, you know, I think there's a lot of different aspects to this that can be explored. And that's something that's really been lacking in this conference. So thank you. Thank you very much. Let me go to Aiden Schaefer, who has his hand up. Aiden, sir?
Hi, Justin. Excellent presentation. What it sparked was a discussion that I had with an engineer from Aerojet Rocketdyne, or Rocketdyne Aerojet, whichever way it's said. Joaquin Castro is the guy's name, and it was at the DCX of 20-year anniversary. And MHD propulsion was something that I was curious about at that time, and started chatting with him. And he said that they had done a lot of test flights and evaluations back in the late 90s. So I didn't see that on your, within the presentation. You were focused more on, like, you know, the quarter horse and some of the newer stuff. So have you looked into their research history is question number one. Question two is a business question. I know Virgin Galactic was trying to partner with Boom Aerospace, and in their like phase 2, they were thinking to do point-to-point supersonic or hypersonic travel. So Virgin Galactic, you know, they're the anchor tenants at the Spaceport America here in New Mexico. And a company like yours would be maybe have a strategic partnership. So those are.
Oh, yeah, thank you, Aiden. I appreciate that. On the first question, I've not specifically seen that research. And if I don't answer this directly, just correct me, Aiden. The flight testing of MHD, or how that would look, is basically there has to be something in addition to the magnetic fields or the lasers. There has to be something else that can provide the power. And the flight testing of that would look kind of similar to what Hermios is doing, but it's going to look slightly different. And that's kind of what I hope to do in a test facility, is kind of scale up. You know, Doug Kodron, the COO at Baldwin, he comes from a research background of small wins, like small scalable wins. So that would relate to a testing cycle of physically building a combustion chamber, the Midnight engine, that can be tested at the flight environments that it might experience. And the things that we're doing, like obtaining higher energy densities, is how we're trying to solve the problems of increasing the flight envelope. Now, correct me if do I need to clarify anything, or?
That's a good answer, but the question was, have you looked into Aerojet Rocketdyne, if you're able to?
Yes.
They have already done test flight campaign in the late 90s, if I remember this discussion correctly.
Yes.
So it was kind of a direct pointing question.
Gotcha. I haven't specifically looked at that.
Okay. And then, yeah, the business question, have you talked with anybody at Virgin Galactic? Like, use phase 2 or second phase lingo if you have or have not. I can help you get in contact with George Whitesides. So that's.
Oh, definitely. I'd be interested in that. I know I've lost people to Virgin Galactic.
Oh, yeah, they're just moving too slow for my liking.
Yeah.
Anyway.
No, I would love that, Aiden. I appreciate that.
Okay. Well.
Yeah. Well, if it's okay, Aiden, I'd like to go to Gary if you're set. And awesome. Thank you, sir. Aiden, thank you. And let me go to Gary, and then we will go to Greg Hodgin for his presentation after that. Again, we're shortening things down a little bit. Gary, go for it, sir.
Yeah, thanks, Justin. Really interesting talk. I had a question related to the bypass. You presented Ajax, which had the MHD bypass. the whole point of which, of course, is to slow down the flow. You take energy out of the flow, slow it down for the combustion chamber, put it back in at the end, right? So that's what's leading to my question about the midnight scramjet. What is the maximum Mach number that internally that the scramjet combustion chamber can tolerate, and does it need MHD bypass?
Yeah. So good question. Thank you, Gary. The idea of slowing the air in like the combustion chamber of scramjet is not new. It's already used with flame holders. So that's Baldwin's approach, is how can we use what's already there, the hypersonic flow, the temperature, the existing scramjet combustion chamber layout. How can we use those principles and then slow the air like you said, and use that?
So does it need MHD bypass or not at this stage?
I think we're looking at both. So we want to apply MHD generation to the combustion chamber, as well as the inlet and the nozzle.
Okay, thank you.
Awesome.
I know that's interesting. MHD generation is not typically thought or applied to the combustion chamber because there's challenges with that. So I'll acknowledge that.
Awesome. Gary, thank you, sir. Let me go to Ross, and then I think we're probably just about out of time. Ross, go for it, sir.
Yeah, I was just curious, like, you're saying it might go at Mach 7. Is that the proposed speed? Like,
Yeah.
what percentage of the force is preventing it from going is aerodynamic drag? Do you know at that speed, like how much is the percentage of the aerodynamic drag preventing it from going faster, holding it back?
Yeah, I think I can talk about I'll just give you an experiment that we did through simulation and reducing the drag. So because I acknowledge, so kind of some of the other questions are, okay, you have to reduce the flow speed, right? So how can you and that's going to create drag. So again, this is a holistic problem. So what we did was look at energy addition towards the inlet nose cone of a body, and using energy addition, you can reduce drag by 30% just with energy addition source. And that related in our tests and our experiment to a 40% reduction in drag, or a 40% increase in range of the hypersonic body. So that the energy used in MHD generation towards the inlet is used to power in the bypass method the nozzle accelerator as well as the ionization source. But that test, does that help? Does that answer the question, Ross?
Yeah, and well, I'm also working with someone right now. We came up with a design that actually appears to not just have a reduced aerodynamic drag, it has zero aerodynamic drag. So it's a weird shape that no matter how fast it goes, it creates a low pressure in the front that actually seems to suck the projectile forward.
Yes.
And as the laminar airflow goes around the body, it has to exactly double the velocity that it's coming in. So it ends up balancing out and creating a higher pressure in the back. So no matter how fast we've pushed air at it, it is zero. I mean,
Yes.
it literally, like we think that this thing could go 1,000,000 miles per hour and would have absolutely no drag whatsoever, as though you're shooting it across space.
Yeah. Well, and Ross, maybe that's something. We're at the top of the hour, and I need to go to Greg. Maybe that's something you could follow up with offline with Justin. Justin, do you think you could put your email in the chat, and then you and Ross could go more on it? Okay. And Ross, let me apologize for cutting you off. I need to put Harold's hand down too. Again, we're going to 1 hour for presentations, and so that's. I'm still kind of getting used to it. Okay, so let me do this. I want to introduce our next presenter. So before we do that, everybody, let's just give another hand to Justin Pearson. And again, everybody, let me apologize for a few bumps on the road. Justin, was a great presentation. I'm still getting used to doing 1 hour presentations instead of 2. And it was just with the 2 hour presentations, what we just didn't have, we didn't have enough people asking enough questions, I guess. So maybe in the future we'll go back to that. But okay, so